So now let's think about rotations, and many of the things we think about here are very, very similar to things that you've already thought about, and it'll be a lot easier if you try to remember those similarities. So when we talk about uh, motion of a rotating thing, and our simple example of a rotating thing will just be a disc here, and the disc lies in the plane of the blackboard, and then it's rotating one way or another about an axis of rotation that is perpendicular to the blackboard, and it right here and it passes right through the middle of the disc. And let's just imagine some counterclockwise rotations. Imagine this arrow is painted on the disc, and in some amount of time it rotates from an initial orientation here to an orientation this way. And the way we talk about displacements and velocities when we're talking about rotations is with angles, angular displacement and angular velocity. Uh, if we're thinking about, say, the tip of this arrow, or really any point along that arrow, we represent its location with an angle, and usually it's angled with respect to the horizontal rightward direction. And these points are an angle that will say theta initial away from uh, our our reference direction, and then rotates counterclockwise until it's rotates from here to here until now these points make an angle this large, theta final, with respect to the reference direction. At we will always define positive when we're talking about rotations. A positive rotation is counterclockwise. So theta final is a more positive, bigger angle, and theta initial is a smaller, less positive angle. So the angular displacement change between the final and initial values of the angle is positive. Right? This is a bigger positive number. This is a smaller positive number. And then we define our angular velocity just the same way that we define regular meters per second velocity, like this. Our symbol for angular velocity is lowercase Greek letter omega. It's omega. It looks like a W, but omega. And we define it as angular displacement divided by the amount of time it took to make that much angular displacement. Just exactly like we define ordinary velocity as ordinary displacement divided by the amount of time it took to make that displacement. The angular velocity is a vector. Uh, it's a vector that always points one way or the other along the axis of rotation. And if it's a counterclockwise rotation, we'll say it points this way. And if it's a counterclockwise rotation, we'll say that the angular velocity points that way. So this number here, what we're really talking about here are magnitudes of the angular velocity, or in other words, angular speed, just how fast it's rotating without regard to whether it's rotating counterclockwise or clockwise. And then we define an angular acceleration in just the same way that we defined ordinary meters per second acceleration. Here it is. Alpha, lowercase Greek letter alpha, is our symbol for angular acceleration, and it's just change in velocity divided by the amount of time it took to make that change, except that it's angular velocity instead of meters per second velocity. So in other words, it looks just like our defining equation that defines ordinary meters per second acceleration. Change in velocity divided by the amount of time it took to make that change. And furthermore, we remember that this delta V, we should think of that delta V as extra velocity added on to the original velocity in order to make the velocity change, because acceleration measures change in velocity. Same thing here. We want to think of delta omega as extra angular velocity added on in order to make angular velocity change, because after all, angular acceleration measures the change in angular velocity. Like I said, this stuff is very, very similar to the way we've already been talking about velocities and accelerations. Just to spell that out, change in anything is just the final value minus the initial value. Or you rewrite that by adding omega initial to both sides of the equation, and then you have omega initial plus this extra angular velocity added on, which we call delta velocity, and that gives us a different final velocity after you've finished adding on all that velocity. So there are basically just four cases here. Moving in the positive direction, and just like with linear velocity and linear acceleration, moving velocity in the positive direction and speeding up, velocity in the positive direction and slowing down, velocity in the negative direction and speeding up, and velocity in the negative direction and slowing down. Let's look at those four cases for rotational situations. So here's our rotating disk, and we'll say it's rotating counterclockwise and speeding up. Well, remember, for a counterclockwise rotation, we always call that kind of thing positive velocity. And as I also said, if you see a counterclockwise rotation, then the angular velocity vector, which always points one way or the other along the axis of rotation, will, in this case, point this way towards you. So what we're really saying is this direction here, perpendicular to the blackboard or perpendicular to the paper. That's the positive direction. And then into the blackboard, obviously, is the negative direction. So positive velocity and speeding up, that means this positive number is getting larger and larger, going, say, from 2 radians per second to 4 radians per second. But in order to get larger and larger in that way, you add positive velocity. That is the extra velocity added on in order to make the disk speed up is positive. But angular acceleration, just like regular meters per second acceleration, angular acceleration points in the same direction as the extra velocity added on. Right? Where have you heard that before? Regular meters per second acceleration points in the same direction as the extra velocity added on. So if the extra velocity added on is positive, that means the acceleration must be positive. Okay, now, next case, imagine same kind of rotation counterclockwise, but now slowing down. Well, or counterclockwise. It's still a counterclockwise rotation, and counterclockwise rotations we always call positive. We're rotational velocity is positive. But now, slowing down, that means that this positive number is getting smaller. And what kind of angular velocity do you have to add to this in order to make this positive number smaller? Well, you have to add on something negative to cancel out some of the positive velocity that you started with. So the extra velocity added on is negative, and so the acceleration is negative because the sign and the direction of any acceleration, whether it's angular acceleration or meters per second acceleration, right, the direction of any acceleration always points in the direction of the extra velocity that is being added on. Now, clockwise rotation and speeding up. So if counterclockwise rotations are defined as positive angular velocity, then the other kind of counterclockwise rotations are defined as positive angular velocity. So clockwise rotations have to be defined as the other kind, the opposite, negative velocity. But it's speeding up, which means going faster and faster in the negative sense, going through more radians of angle per second in the negative sense. So initially the angular velocity might have been, let's say, 1 radian per second. That is, you sweep through 1 radian of angle while moving in the negative direction. And then later on, it becomes, say, negative 2 radians per second. You sweep through 2 radians of angle while moving in the negative sense. In other words, if you're moving in a negative way and speeding up, you're having more and more negative velocity added on. I previously just say 1 radian per second while moving negative, and then speeding up would mean 2 meters per second while moving in the negative sense. That is a velocity of negative 2. So negative angular velocity is added on in order to make velocity that was already negative even more negative. You now have stronger negative velocity. You have a negative velocity with a bigger magnitude. And of course, what is magnitude of a velocity? It's speed. So so by adding additional negative velocity to velocity that was already negative, you get stronger negative velocity, higher speed, in other words. But adding negative velocity is indicated by a negative acceleration. Acceleration and the velocity added on always point the same way. And then the final case, clockwise rotation, but slowing down. Still clockwise rotation, we define counterclockwise as positive spin and positive velocity. So clockwise is negative spin or negative velocity. But it's slowing down, which means you have less and less negative motion as time goes by. Say an earlier velocity might have been negative 2 radians per second, and then later on it's just negative 1 meter per second. How do you get from negative 2 to negative 1? You get there by adding positive 1. When you've got negative velocity and slowing down, you think of that as happening because the extra velocity added on is positive. Right? This positive velocity added on cancels out some of the negative velocity that you started with, so that in the end you have less of that negative velocity. That is, you're moving slower in the negative direction. Whereas before you added this on, you were moving faster in the negative direction. And again, velocity added on and acceleration point in the same direction. So positive acceleration. Now, to sum all this up, we can make two statements that we've already made, you should already be familiar with in the context of regular meters per second velocities and regular meters per second accelerations. Here, velocity and acceleration have the same sign, and the disk is speeding up, spinning faster. And here, velocity and acceleration have the same sign, and the disk is speeding up, spinning faster and faster. So, what do we say? Keep this for a second. If you're speeding up, that means velocity and the acceleration point in the same direction. Direction might be positive or the direction might be negative. As long as they're pointing in the same direction, that always corresponds to speeding up. And then look at these two cases now. Here, positive velocity, negative acceleration. Velocity and acceleration point in opposite directions and the thing is slowing down. And here, negative velocity and positive acceleration. Again, velocity and acceleration point in opposite directions and the thing is slowing down. The rate of spinning is decreasing. So, we can say that whenever you're slowing down, velocity and acceleration must point in opposite directions. Velocity and acceleration must point in opposite directions. And we've already known that in the case of ordinary velocity and ordinary acceleration. When velocity and acceleration point the same way, that always corresponds to speeding up. When they point opposite directions, that always corresponds to speeding down. So if you see something speeding up, then you know velocity and acceleration point the same way, but the logic works the other way around. If you know velocity and acceleration point the same way, then you expect to see them speeding up. So the logic works this way as well as this way. So really should have the double-sided arrows for this implies this, but this also implies this. Works either way. And now, yet another similarity between velocities and accelerations and angular velocities and angular accelerations. Remember Newton's second law. The main idea of Newton's second law is that accelerations happen only if there's a net force acting on the object. Net force, non-zero net force, is the cause of acceleration. Similarly, there's going to be some kind of a cause for angular acceleration. There's going to be something like forces and net force that will cause angular acceleration. So let's write that out. If the net force on an object is not zero, or to put it another way, if there is net force, then that implies there is acceleration, or acceleration is not zero. Or other way around, if you notice that an object is accelerating, that it has non-zero acceleration, then that implies the net force must be not zero. Must be some real net force present. And then we have something that plays the same role with rotational accelerations that force does with ordinary accelerations, and we call that thing a torque. And we use this Greek letter, lowercase Greek letter tau, to symbolize torque. Like force, torque is a vector, and just like what Newton's second law says, if there is a net torque, whatever that means, acting on some object, or net torque is not zero, then you know there's going to be rotational acceleration, angular acceleration, or angular acceleration is not zero. And similarly, if you notice that some rotating object is changing its rotational state, like spinning faster or spinning slower, that is, if you observe that there is non-zero angular acceleration, then you know that that's happening only because there is a non-zero torque acting on the object. Okay, so that's what torque does. But next question is, what is a torque really, or how is a torque produced? Well, to have a torque, you need a force, but the force has to act in just a specific, special kind of way in order to actually make a torque. And that's best to talk about that in a specific example here. Let's say you're trying to open a door. The door is just stationary right now, but now you're going to push on the doorknob and make the door start to rotate. In other words, you're changing the rotational velocity of the door. When the door is just sitting still, it has obviously a rotational velocity of zero. Then you push it and it starts to rotate about the hinges. Now it's got a non-zero rotational velocity. You've changed the angular velocity from zero to something other than zero. In other words, the door has had an angular acceleration. Its angular velocity has changed. And so a torque caused that change in the angular velocity. A torque caused that angular acceleration. So let's look at the door from above. Here's the hinge, here's the door, and then here's the doorknob. And one important factor here, imagine a displacement vector that takes you from the hinge to the place where my force will be applied. I'm going to push on the doorknob. I'm pushing on the doorknob in that direction now. And this is a displacement vector that starts here and always ends up wherever the force is applied. So being a displacement vector, I'll call it D. Book does something a little bit different, but I like to think of this as it makes more sense to me to think of this as a displacement vector, so I'll label it with a D. Now, that's a situation where you get a torque, and you can always calculate the amount of torque you get, the strength of torque you get, the magnitude of torque with this equation. One factor is the strength or the magnitude of the force. Kind of makes sense. The next factor is just the magnitude of that displacement vector. then there's a third factor, sine of an angle. And the angle is always the angle between the displacement direction and the force direction. So in this particular case, there's the angle theta. And that's how you get a torque. You apply a force, but in order to have torque, right, these two terms have to be non-zero also. Now, whenever we talk about a torque, we're always talking about torque with respect to a reference point. And by reference point, I mean just some point anywhere that you're free to choose anywhere, but then the displacement vector is always defined in terms of that reference point. What I did here was choose the hinge for the reference point. Commonly, it makes most sense. It's easiest to understand if you choose the axis of rotation for your reference point. But in fact, as we'll see in more detail how this really works later on, in fact, you're free to choose a reference point absolutely anywhere. But wherever you choose your reference point, you're always going to be imagining rotations as if that reference point were the axis of rotation, right? I choose my reference point here because this point really is the real axis of real rotations. That's why I said it makes most sense. But we'll look at other ways of doing it. We'll look at other ways of doing it later on. So anyway, that's how torque works. Let's look at a few different ways that you might push on the door in order to open the door. So I'll just write the torque rule up here for handy reference. So here's one way to open the door. I push perpendicular to the door and I push right at the doorknob. So my displacement vector always goes from my reference point, and like I said, I'm choosing the reference point to be where the actual axis of rotation is, and the displacement vector always moves from the reference point to wherever the force is applied. So then the magnitude of the torque is just the magnitude of the force times the magnitude of the displacement, which in this case is just the same as the width of the door. Let's call that distance L. And then the angle here in the sine is angle between displacement direction and force direction. Displacement points right along the door. Force is perpendicular to 90 degrees. So we've got sine of 90 degrees. Trigonometry tells us that the sine of 90 degrees is 1, plus 1. So torque in this case is just magnitude of the force times the L meters for the width of the door. I'll call this situation A. Now, imagine something a little bit different. Imagine that I'm still pushing at the doorknob, but now I'm not pushing perpendicular, I'm pushing at an angle. So, the door, same door, I'm still pushing right here on the same point. So the displacement vector that takes me from the reference point to the point where the force is applied is the same displacement. same reference point, same displacement vector, but now the force, we'll say the force is just as strong, but now it's pointing in a different direction. Not perpendicular. So now there's the angle between the displacement direction and the force direction, not 90 degrees anymore. So now in this case, the torque, call it case B, is still magnitude of the force times the magnitude of the displacement vector, which is still L, times sine of this angle. Well, trigonometry tells us that any angle less than 90 degrees has a smaller sine than the sine of 90 degrees. But sine of 90 degrees, which is 1 is the maximum possible value for a sine or a cosine. So angles less than 90 degrees have sines less than 1. So the sine factor in this case is smaller than the sine factor in this case. Let's say, just to be specific, let's say this is 60 degrees. The sine of 60 degrees is about 0.87. So in other words, if we don't push perpendicularly, if we push at some angle other than perpendicular, right, we get a smaller torque. This torque is only 87% as strong as this torque. Torques cause angular accelerations, so less torque means less angular acceleration. The door opens more slowly. Or to put it another way, it's harder to open the door. And then in case, here's one more example. Call it case C. Same door, same width, same doorknob, same force. And again, I'll go back to the force pointing perpendicular to the door, but now I'll push right in the middle of the door. So right here in the middle of the door is the point where the force is applied. So now, keep the reference point at the same place. Now the displacement vector takes us from the reference point to the point where the force is applied, as always, but now that displacement vector is only half as large as it was before. And then the angle between the displacement vector and the force direction is now back to 90 degrees. So in case C, the strength of torque C is equal to strength of the force, magnitude of the displacement vector, which is only half of what it was before, or L over 2 meters, times sine of this angle, which is 90 degrees. Sine of 90 degrees is 1. So torque C is just, strength of torque C is equal to strength of the force times L over 2. In other words, smaller torque than either case A or case B. And that makes sense because we put the doorknob out here because pushing out here at the doorknob makes it easier to open the door. Now you see why. Pushing out here instead of pushing back here, pushing out here gives you a bigger torque because that displacement vector is bigger. And bigger torque means more angular acceleration. The door speeds up quicker and opens more easily. Now, last example, an extreme case, which actually is kind of important, even though at first it might seem kind of silly. Same door, same reference point. Now I push right at the hinge. And you know what's going to happen there, obviously. Nothing will happen. The door won't start rotating. In other words, it maintains a constant angular velocity, constantly zero. But constant velocity means zero acceleration. Constant angular velocity means zero angular acceleration. And if there is no angular acceleration, that's because there is no torque. If there is torque, there must be angular acceleration. So if there's no torque, there won't be angular acceleration. And we can see why there's no torque in this case. Case D. Go back to the equation for calculating strength of a torque. It's strength of the force times the magnitude of the displacement vector times sine of the angle, but that's zero. Because remember what the displacement vector D is. It's a displacement that starts at the reference point and then moves to the point where the force is applied, but in this case, they're the same point. So in this case, it's zero displacement. The starting point, the reference point, and the ending point, the point where the force is pushing, are the same point. So you don't have to go through any displacement at all to get from the reference point to the point where the force is applied. Zero displacement. So this factor is zero, so torque is zero. And no torque means no rotational acceleration, no angular acceleration. The door stays put. All right. Now, one other thing we need to think about directions of torques. Just like we have to pay attention to whether forces are positive or negative so that we can add them up correctly when we're trying to see what the net force is like. Same thing here. We have to pay attention to what torques are positive, what torques are negative in order to add them up correctly. And it's a pretty simple rule. And it works very similarly to the relationship between net force and regular acceleration. Right? We know that according to Newton's second law, net force and the acceleration that that net force causes must always point in the same direction. Net force doesn't necessarily point in the same direction as the velocity, might or might not, but for sure always net force points in the same direction as the acceleration. And similarly, the thing that causes angular accelerations, net torque, and that angular acceleration point in the same direction. So in other words, the sign or the direction of angular acceleration is the same as the sign or direction of the torque that caused it. So for example, let's go back to this case. Counterclockwise rotation speeding up. Counterclockwise rotation is defined as a positive rotational velocity, but speeding up means you're getting more and more of that same kind of velocity. You're adding more and more velocity of the same kind. Acceleration points in the same direction as the velocity added on. And of course, if you're speeding up, velocity and acceleration point the same way. So in this case, the torque that is causing this kind of angular acceleration points the same way as the acceleration. Positive net torque. Or to just say it more simply, anytime more positive spin is added to any kind of rotation, it was a positive net torque that did that. And then one other example here, let's say, again, counterclockwise rotation, slow down. By the way, this kind of situation was what happened when I was opening the door. I was making a counterclockwise rotation up here that wasn't there before. I was making counterclockwise velocity. I was making positive angular velocity up here that wasn't there before. I was adding in positive angular velocity. The angular acceleration was positive, in other words, and it has to be a positive torque that caused that. Slowing down, on the other hand, it's counterclockwise, so that's still defined as a positive angular velocity, but this positive number is getting smaller and smaller as time goes by because the extra velocity that's added on is negative, subtracting away from however much angular velocity you started with. So angular acceleration is negative because it points in the same direction as the velocity added on, or since you're slowing down, you know velocity and acceleration must be opposite. So the net torque that caused that acceleration the net torque that caused that acceleration must be negative. Okay, now in a little bit I'll have one more, well, I'll see if I can fit that in right here. One more thing to show you. The battery on my computer is running low, so I've got to hurry here a little bit. Let's think about this. Say I'm holding onto a stick, holding on at this end, and then there's some mass hanging from that stick. So because there's this mass hanging, there's tension in this string, and that tension is pulling down on this end of the stick. And so because of this tension, there's a torque, and that torque would make this stick start to rotate clockwise. Remember, making clockwise rotations appear means you're adding in negative angular velocity, and if you're adding it, and if the velocity added on is negative, that's negative angular acceleration, and negative angular acceleration is caused by a negative torque. So this force would cause a negative torque. Except I can apply a counteracting torque here at the other end to keep the stick stationary and not rotating. But how much torque do I have to apply? Well, I have to apply the opposite kind of torque, but just as strong. So how strong is this torque? Well, make this the reference point, because if the stick were to rotate, you can easily think of it as rotating about that point. So we'll say that there's the displacement vector that takes us from the reference point to the point where the force is applied. And let's say the stick is oriented 30 degrees away from horizontal. So now we've got all the information we need in order to figure out how much torque this is producing. The magnitude of the torque produced by the tension is just the strength of the force times the magnitude of the displacement vector, which in this case is just going to be the length of the stick, so I'll call it L meters, times sine of the angle between the displacement vector's direction and the force direction. Now here's the important point that I really wanted to emphasize here. Stop and think carefully before you put a number in this slot. Don't just put in a 30 because you see a 30 degrees in the diagram. Stop and think, what is the angle between the displacement direction and the force direction? Well, the displacement direction is this way. The force is straight down. So that is the angle between the displacement direction and the force direction. That's 60 degrees. The angle there, to get the correct torque, the angle there must be 60 degrees, not 30. So in this case, the magnitude of the torque would just be strength of the tension, length of the stick, times sine of 60. You saw that a few minutes ago, 0.87. Okay, so now there are a few problems for you to try out and see how you can do with them.